For centuries, humanity has searched for life by looking inward, first to Earth's own past, then to nearby planets, then to distant worlds orbiting stars inside our galaxy. We ask whether Mars was once alive, whether oceans hide beneath the ice of Europa, whether rocky planets around distant suns might resemble our own. But all of these questions quietly assume something we rarely stop to examine, that the galaxy itself does not matter, that if a planet has the right temperature, the right chemistry, and the right star life will simply follow, as if every galaxy offers the same chances, as if the universe treats all its cosmic neighbourhoods equally. Yet galaxies are not interchangeable backdrops. They are not passive containers for stars and planets. Each one carries a unique history written across billions of years, a history of violence or calm, of radiation or silence, of chaos balance and long periods of fragile stability. Some galaxies burn fast and bright, flooding their worlds with deadly energy. Others grow slowly, quietly, enriching themselves with the elements life needs to begin. Some are shaped by endless collisions. Others drift through cosmic time almost untouched. If life depends on time stability and the right materials, then the question changes. Not just can life exist elsewhere, but where does the universe make it easiest for life to begin at all? Tonight we step back from planets, we step back from stars, and we ask a deeper question, one that stretches across the entire cosmos. Are some galaxies better at creating life than others? To answer that question, we need to change how we think about life in the universe. For most of human history, the search for life followed a simple logic. Find a planet like Earth, place it at the right distance from a star, add water chemistry and time, and life we assume will emerge. This approach treats planets as isolated worlds shaped only by their stars. But in reality, no planet exists alone. Every star, every planetary system is embedded within something far larger. A galaxy? Galaxies determine how stars are born, how often they explode, and how violently their environments change over time. They control the flow of radiation that sweeps through space. They regulate how quickly heavy elements are produced and recycled. They decide whether a young world will enjoy billions of calm years or be repeatedly stripped, irradiated, and reset. In some galaxies, stars form in relentless bursts. Supernovae erupt in rapid succession. Radiation saturates entire regions, tearing apart fragile atmospheres before chemistry can organize itself. In others, star formation slows to a quiet rhythm. The universe there moves patiently. Elements accumulate gradually. Planets orbit stars that change little over immense spans of time. From the perspective of life, these differences are everything. A planet does not need perfection. It needs continuity, long stretches of relative calm where complexity can build layer by layer without being erased. And that calm or its absence is not decided by the planet. It is decided by the galaxy that surrounds it. This realization forces us to rethink one of our deepest assumptions. Perhaps the universe is not uniformly friendly to life. Perhaps some galaxies are naturally hostile no matter how many planets they contained, and perhaps others quietly provide the conditions where life can take hold more easily and endure longer. Before we can search for life across the universe, we must first understand the environments that shape it. To do that, we need to look back to the moment humanity first realized that galaxies themselves were not all the same. The night sky once felt complete, a luminous band arced overhead, steady and familiar, as if all the stars belonged to a single vast structure. Beyond that glowing river of light, astronomers saw little reason to expect more. Then something refused to fit. Through increasingly powerful telescopes, faint spiral shapes appeared scattered across the sky. They were called nebulae, ambiguous objects whose nature no one could agree on. Some believed they were nearby clouds of gas still forming stars. Others suspected something far more distant and far more unsettling. The argument was not philosophical. It was measurable. When Edwin Hubble examined one of these spirals, a subtle detail changed everything. Inside Andromeda, individual stars could be resolved. Some of them brightened and dimmed in a precise rhythmic pattern. Those rhythms were already understood. They belonged to Cepheid variable stars objects whose intrinsic brightness made them reliable cosmic yardsticks. By measuring their cycles, Hubble calculated their true distances. The numbers left no room for interpretation. Andromeda lay far beyond the boundaries of the Milky Way. It was not part of our galaxy. It was another galaxy entirely. With that realization, the universe shattered its old limits. The Milky Way became one island among countless others. Each galaxy emerged as a self-contained system shaped by its own gravity, chemistry, and evolutionary history. This was not just an expansion of scale. It was a redefinition of environment. Galaxies could now differ in fundamental ways. Some would form stars, rapidly flooding space with radiation. Others would evolve, slowly preserving calm conditions for immense spans of time. Some would collide repeatedly, reshaping themselves through violence. Others would drift almost untouched through cosmic history. And with that diversity came an unavoidable implication. If galaxies evolve differently, then the conditions they create are not equal. And if life depends on those conditions, then life itself may be unevenly distributed across the universe. The discovery of other galaxies did not simply multiply the number of stars, it multiplied the number of cosmic experiments. To understand where life might arise, we must first understand the environments that run those experiments. And that means learning to see galaxies not as distant shapes, but as dynamic ecosystems, each with its own rules. Galaxies are often described as collections of stars, but that description misses what truly matters. A galaxy is not just a container, it is an environment. Inside it, stars are born at different rates. They live for different lengths of time. They explode with different frequencies. And together these processes shape everything that happens to the worlds orbiting them. In this sense, a galaxy behaves less like a backdrop and more like an ecosystem. On Earth, ecosystems determine what kinds of life can exist. A rainforest supports complexity through abundance and constant recycling. A desert limits life through scarcity and extremes. The deep ocean favors organisms adapted to darkness, pressure, and isolation. The same principle applies on a cosmic scale. Some galaxies resemble turbulent ecosystems. Stars form rapidly, crowding together in dense regions. Supernovae erupt, often filling space with radiation and shock waves. The environment is energetic, productive, and relentlessly disruptive. Other galaxies evolve more quietly. Star formation proceeds at a measured pace. Explosions are rare. Radiation levels remain moderate for billions of years. From the perspective of life, these differences are decisive. Life does not require perfection. It requires consistency, the chance for complex chemistry to build, survive, and adapt without being erased. And that opportunity is shaped long before the first planet forms. It begins with how a galaxy manages energy. Some galaxies flood their interiors with ultraviolet light and cosmic rays. Others allow energy to flow more gently, giving planetary atmospheres time to stabilize. Some recycle heavy elements, efficiently enriching future generations of stars. Others lose that material to space, limiting what planets can become. These are not minor variations. They define whether a galaxy becomes a hostile arena or a long-term refuge for complexity. What makes a galaxy life-friendly is not a single feature, but a balance. Energy must be present, but not overwhelming. Heavy elements must exist, but not be locked away too early. Change must occur, but slowly enough for stability to emerge. In violent galaxies, this balance collapses. Rapid star formation saturates space with radiation. Frequent supernovae strip atmospheres and destabilize planetary orbits. Any fragile chemistry that begins to assemble is repeatedly erased. In overly quiet galaxies, a different problem appears. Star formation slows to a crawl. Fewer supernovae occur, limiting the creation and distribution of heavy elements. Planets may form, but without the materials needed for magnetic fields, tectonics, or long-term climate regulation. Life depends on a narrow window between these extremes. Galaxies that evolve at a moderate pace allow complexity to accumulate. They recycle material without constant destruction. They provide steady energy without overwhelming disruption. This perspective reframes the search for life. Instead of asking whether individual planets are habitable, we must ask whether their galactic environment allows habitability to persist. A planet can have water, the right temperature, and a stable star, yet still be doomed by the galaxy it inhabits. A nearby supernova can sterilize its surface. A burst of radiation can strip its atmosphere. A galactic merger can destabilize its orbit entirely. From this view, habitability is not a local property. It is a product of galactic-scale processes unfolding over billions of years. Some galaxies naturally support this balance, others destroy it repeatedly. And that leads to a crucial realization. Before we compare planets or even stars, we must first compare galaxies themselves. Only then can we begin to identify which cosmic environments truly give life a chance. When we talk about life in the universe, the conversation often narrows too quickly. We list ingredients, liquid water, organic molecules, a planet in the right temperature range, but these are surface conditions. They describe what life uses, not what life truly depends on. At a deeper level, life is a process, a slow accumulation of complexity that unfolds over immense spans of time. And for that process to begin and survive, several requirements must align long before biology appears. The first is time. Life does not emerge quickly. On Earth, it took hundreds of millions of years for the earliest chemistry to organize into something capable of replication. Billions more were required for complexity to grow, adapt, and diversify. Any environment that resets too often erases progress. Any region that changes too violently cuts evolution short before it can gain momentum. The second requirement is stability, not absolute calm but predictable change. Stars that shine steadily rather than flaring unpredictably. Radiation levels that remain within tolerable bounds. Gravitational conditions that allow planetary orbits to persist for billions of years. Without this stability, chemistry becomes fragile. Molecules break faster than they can assemble. Atmospheres erode before ecosystems can take hold. The third requirement is material. Life, at least as we understand it, depends on heavy elements. Carbon to form complex chains, oxygen and nitrogen to drive chemistry, iron and radioactive elements to power planetary interiors and magnetic fields. These elements do not exist in the early universe. They are forged slowly inside stars and scattered through space by stellar death. A galaxy that produces heavy elements too slowly starves future planets of complexity. One that produces them too violently may destroy the very environments those elements could have supported. From the start, life is caught between creation and destruction. These requirements, time, stability, and material do not arise by chance. They are not properties of individual planets. They are outcomes of the environments in which those planets form. A planet cannot choose how often nearby stars explode. It cannot control how quickly heavy elements accumulate around it. It cannot shield itself from galactic-scale radiation or gravitational upheaval. Those conditions are set by the galaxy. In galaxies where stars form rapidly, supernovae arrive in waves. Radiation spikes repeatedly. Planetary atmospheres are stripped, rebuilt, and stripped again. Any early chemistry is forced to restart from scratch. In galaxies where star formation nearly stops, stability returns, but at a cost. Few new stars form. Few heavy elements are produced. Planetary systems that do emerge may lack the internal heat magnetic shielding or chemical richness needed for long-term habitability. Life then requires a galaxy that evolves at the right pace, fast enough to enrich itself with heavy elements, slow enough to avoid constant destruction. This balance is rare. It is not guaranteed by size, brightness, or age. It depends on how a galaxy manages its energy, its material, and its history across billions of years. Only certain types of galaxies naturally maintain this balance. Others swing too far toward chaos or stagnation. With this foundation in place, we can finally begin to compare galaxies directly, not by how beautiful they appear through telescopes, but by how well they create the conditions that allow life to persist. The first and perhaps strongest candidates are spiral galaxies. Among all the galaxies we observe, spiral galaxies occupy a unique middle ground. They are neither quiet relics of the early universe nor violent engines of constant destruction. Instead, they evolve in measured cycles, balancing creation and disruption across billions of years. A spiral galaxy organizes its stars into sweeping arms that rotate slowly around a dense core. Within those arms, gas clouds collapse, stars are born, and heavy elements are forged. But this process is not uniform. Star formation rises and falls, creating a rhythm rather than a constant storm. For life, that rhythm matters. In spiral galaxies, stars are spaced far enough apart to reduce the frequency of catastrophic events. Supernovae occur, but not in relentless waves. Radiation levels fluctuate but rarely remain extreme for long periods. This allows planetary systems to survive long enough for atmospheres to stabilize and chemistry to persist. The Milky Way is a textbook example. It is massive enough to retain heavy elements, yet not so dense that stars crowd dangerously close. Its star formation rate has remained moderate for billions of years. Violent bursts occurred in its distant past, but long stretches of calm followed long enough for complex life to take hold on at least one planet. Other spiral galaxies share similar traits, sometimes to an even greater degree. Andromeda, for instance, forms stars more slowly than the Milky Way. Its radiation environment is generally calmer. Its habitable regions may stretch wider, offering more stable zones where planetary systems can remain undisturbed for immense spans of time. This balance between activity and restraint is not accidental. Spiral galaxies regulate themselves through rotation. As they spin, material spreads outward rather than collapsing entirely toward the center. This prevents runaway star formation and limits the frequency of destructive events. The result is a galaxy that evolves steadily rather than violently. From a biological perspective, this steady evolution is invaluable. Life does not thrive in constant extremes. It needs environments that change slowly enough for adaptation to keep pace. Spiral galaxies provide exactly that, long-term continuity punctuated by manageable disruption. But even within spiral galaxies, conditions are not uniform. Closer to the galactic center, stars cluster tightly. Radiation increases. Supernovae become more frequent. Gravitational tides grow stronger, destabilizing planetary orbits. Farther out, conditions reverse. Space grows quieter, but heavy elements become scarce. Planets may form, yet lack the materials needed for strong magnetic fields or geological activity. Between these extremes lies a narrow region where balance is restored. A region where stars are stable elements, are abundant, and catastrophic events are rare enough to allow complexity to survive. This realization leads to one of the most important concepts in astrobiology. Even in the most life-friendly galaxies, only certain regions truly support long-term habitability. Even within a galaxy that seems friendly to life, habitability is not evenly distributed. From a distance, a spiral galaxy may look calm and balanced, but inside it conditions change dramatically with location. Radiation levels rise and fall. Star density shifts. The availability of heavy elements varies across vast distances. These differences matter. They led astronomers to propose a powerful idea, the galactic habitable zone. The concept is simple, but its implications are profound. Just as planets have habitable zones around stars, galaxies may have regions where life has the best chance to survive over billions of years. Near the center of a spiral galaxy, conditions are extreme. Stars crowd together. Supernovae occur frequently. Radiation from massive stars and the central black hole saturates the surrounding space. In these regions, planets face constant danger. Atmospheres are stripped by energetic events. Gravitational tides distort orbits. Even if life begins, it is unlikely to endure long enough to grow complex. Move too far in the opposite direction and a different problem emerges. At the outer edges of a galaxy, space becomes quiet. Supernovae are rare. Radiation levels drop. But so does chemical richness. Heavy elements become scarce. Rocky planets may struggle to form. Those that do may lack iron-rich cores, magnetic fields, or long-term geological activity. Without these features, atmospheres erode slowly, climates drift, and stability fades. Between these extremes lies a narrow band, a region far enough from the galactic core to avoid constant radiation, yet close enough to benefit from billions of years of chemical enrichment. This is the galactic habitable zone. In the Milky Way, this zone forms a rough ring, neither central nor peripheral. It is here that star density remains moderate. Supernova rates stay low enough to allow continuity. Heavy elements exist in sufficient quantities to build complex planets. Earth resides within this band. But the galactic habitable zone is not fixed. It shifts over time. As galaxies evolve, star formation migrates. Metallicity increases. radiation environments change. Early in the Milky Way's history, the habitable zone was narrower and closer to the center. Over billions of years, it expanded outward as heavy elements accumulated and conditions stabilized. Other spiral galaxies follow similar patterns but not identical ones. In Andromeda, the habitable zone may be broader shaped by its slower star formation and calmer radiation environment. In smaller spirals, the zone can be compressed, squeezed between violent inner regions and chemically poor outskirts. This reveals a critical insight. A galaxy does not offer life a single opportunity. It offers windows that open and close as conditions shift. Worlds that form too early may face radiation and instability. Worlds that form too late may lack the energy and materials life needs. Life then is not just about being in the right place. It is about being there at the right time. And even in the most promising galaxies, those opportunities are limited. Understanding the galactic habitable zone helps us narrow the search, but it also raises a deeper question. If spiral galaxies host these balanced regions, what about galaxies that lack them entirely? To answer that, we must turn to systems that appear calm, ancient, and deceptively stable. Elliptical galaxies. At first glance, elliptical galaxies seem almost ideal. They are dominated by old stars. Star formation has largely ceased. Supernovae are rare. Radiation levels remain low and predictable over immense spans of time. Compared to the dynamic arms of spiral galaxies, ellipticals appear serene, almost frozen in cosmic time. For life, that calm seems promising. Long-lived stars shine steadily. Violent events are infrequent. Planetary systems that survive the early history of the galaxy may enjoy billions of uninterrupted years. Yet this apparent stability hides a fundamental limitation. Elliptical galaxies are quiet because they are exhausted. Most formed early in the universe, often through violent mergers that consumed or expelled their gas. After those chaotic beginnings, little raw material remained to form new stars. With star formation largely shut down, the internal engines that produce and recycle heavy elements slowed dramatically. This creates a paradox. Elliptical galaxies offer stability but lack renewal. Heavy elements exist, but they are locked into ancient stars. Few new planetary systems form, and those that do emerge tend to orbit stars that formed when the universe itself was younger, poorer in metals and less hospitable to complex chemistry. Planets in these galaxies may face subtle but critical disadvantages. Iron-poor cores struggle to sustain magnetic fields. Reduced radioactive heating weakens geological activity. Atmospheres thin, slowly unprotected from stellar winds over billions of years. Life may begin under such conditions, but sustaining it becomes increasingly difficult. There is another complication. Elliptical galaxies often reside in dense environments. They are common in galaxy clusters where gravitational interactions and high-energy intra-cluster plasma shape their evolution. Even if internal conditions remain calm, external forces can introduce long-term instability. Gas can be stripped away. Radiation from surrounding galaxies and hot cluster media can alter planetary environments over time. From a biological perspective, elliptical galaxies may offer too much of one thing and too little of another. They provide time. They provide calm, but they may fail to provide the ongoing chemical and geological activity that life requires to remain resilient and adaptable. This leads to an uncomfortable possibility. The quietest galaxies in the universe may not be the best places for life, not because they are hostile, but because they are incomplete. Life needs more than silence. It needs renewal. And where renewal returns, chaos often follows. To understand where that balance breaks down entirely, we must examine galaxies that swing to the opposite extreme systems, defined not by calm, but by excess. Galaxies that burn too brightly too quickly. Starburst galaxies. If elliptical galaxies suffer from too little activity, starburst galaxies represent the opposite extreme. These systems are defined by excess. In starburst galaxies, stars form at extraordinary rates. Gas clouds collapse rapidly. Massive stars ignite in dense clusters. Supernovae erupt in relentless succession. For brief periods in cosmic time, these galaxies shine with overwhelming intensity. From a distance, they appear productive factories of stars and heavy elements. but from the perspective of life, they are among the most hostile environments in the universe. Radiation floods entire regions, ultraviolet light strips atmospheres, cosmic rays penetrate planetary surfaces, shock waves from nearby explosions disrupt planetary orbits and sterilize emerging chemistry. Any world attempting to nurture life in such a galaxy faces constant interruption. Even if a planet forms with water, a stable orbit, and the right chemistry, it rarely enjoys continuity. Before complexity can accumulate, the environment resets. Again and again. Starburst phases are often triggered by violence. Galaxies collide. Gravitational forces compress gas. Star formation accelerates dramatically. These interactions reshape entire systems. Spiral arms twist and break. Planetary systems are perturbed or destroyed. Central black holes awaken, flooding their surroundings with high-energy radiation. From the outside, these galaxies look spectacular. From the inside, they are catastrophic. Yet starbursts are not permanent. They are brief episodes, tens or hundreds of millions of years long. After the gas is consumed or expelled, activity slows. The galaxy cools, radiation fades. In some cases, this aftermath creates calmer regions enriched with heavy elements forged during the burst. This introduces a subtle possibility. Starburst galaxies may be terrible places for life to begin, but not necessarily terrible forever. Once the chaos subsides, enriched material may settle into new configurations. Stars formed after the burst may enjoy quieter environments. Planets emerging late in the galaxy's history could inherit the chemical benefits without enduring the violence that created them. Still, this path is narrow. The timing must be precise. Too early and life is erased. Too late and energy and material may be gone. In most cases, starburst galaxies spend too little time in this balanced state to matter biologically. They remind us of an important lesson. Creation alone is not enough. A galaxy can be extraordinarily productive and still be hostile to life. Energy without restraint destroys complexity. Violence without recovery leaves nothing stable behind. To find environments where life might quietly endure, we must look away from the brightest systems and toward the smallest and least conspicuous. Galaxies that rarely make headlines. Galaxies that evolve slowly, quietly, and almost unnoticed. Dwarf galaxies are easy to overlook. They are small, faint, and often lost among the brilliance of larger systems. Some contain only a few billion stars, tiny by cosmic standards. Many orbit massive galaxies shaped and distorted by their gravity. For a long time, they were dismissed as biologically irrelevant, too small, too poor in heavy elements, too fragile to sustain complex environments. Yet when viewed through the lens of habitability, dwarf galaxies reveal a different story. Their greatest weakness is also their greatest strength. Dwarf galaxies form stars slowly. Many experience long periods of near silence interrupted only by occasional bursts of activity. Supernovae are rare. Radiation levels remain low for immense spans of time. From the perspective of life, this quiet matters. Complex chemistry does not thrive in chaos. It thrives where change is slow and predictable. In dwarf galaxies, planetary systems may enjoy uninterrupted stability for billions of years. This stability comes at a cost. Heavy elements are scarce. Rocky planets may be fewer. Worlds that do form may lack the iron-rich cores needed for strong magnetic fields or sustained geological activity. But scarcity does not mean impossibility. Even a small number of supernovae can enrich local regions. Planet formation does occur, especially around long-lived low-mass stars, and with fewer nearby explosions, atmospheres may persist longer than in more crowded galaxies. There is another advantage. Dwarf galaxies are often isolated. They reside in quiet regions of the cosmic web, far from dense clusters and frequent galactic encounters. Without constant gravitational disturbance, planetary orbits remain stable over extraordinary periods of time. This isolation creates rare conditions. A planet in a dwarf galaxy may experience fewer catastrophic resets than one in a larger, more active system. Its evolutionary path may be slow but uninterrupted. Life in such environments might not be abundant. It might not be diverse. But if it appears, it may persist longer than expected. This challenges a common assumption. Bigger galaxies are not automatically better. Brighter systems are not necessarily more hospitable. Sometimes life may prefer the quiet corners of the universe, yet even in the calmest galaxies, one factor remains unavoidable. Time. Life does not merely require a stable place. It requires enough time for complexity to accumulate before conditions change. And time, more than any other factor, is shaped by the evolutionary history of a galaxy. To understand that influence, we must step back and examine time itself as a cosmic filter, more than temperature, more than chemistry, more than distance from a star. Life depends on time, not just time to exist, but time without interruption. Time measured not in years, but in billions of years of relative continuity. On Earth, life did not emerge quickly. The planet formed, cooled, and stabilized. Oceans condensed. Chemistry experimented endlessly. It took hundreds of millions of years before the first simple life appeared, billions more before complexity emerged, and all of it depended on one fragile condition. Nothing erased the progress. This makes time the ultimate filter for habitability. A galaxy can contain countless planets. It can possess abundant heavy elements. It can even host stable stars. But if its history is too violent, life never gains momentum. Galaxies are not static. They evolve through cycles of calm and catastrophe. They collide and merge. They experience bursts of star formation. Their central black holes awaken flooding space with radiation. Gases consumed, expelled, or rearranged. Each of these events resets the biological clock. A nearby supernova can sterilize planetary surfaces. A galactic merger can destabilize orbits across entire regions. A prolonged active phase can strip atmospheres beyond recovery. Life does not recover easily from resets. Chemistry must restart. Evolution must begin again. Any complexity that took millions of years to assemble is erased in moments. Galaxies that change too often rarely allow life to advance beyond its earlier stages. In contrast, galaxies with long, uneventful histories provide something invaluable: continuity. They allow planets to remain stable for billions of years. They permit chemistry to explore slowly accumulating information rather than losing it. They give evolution time to refine complexity instead of rebuilding it. This does not mean that calm galaxies are perfect. Small disruptions still occur, supernovae still happen, radiation still fluctuates, but the pace matters. Life can adapt to gradual change. It cannot adapt to constant catastrophe. When we compare galaxies through this lens, a pattern emerges. The best environments for life are not the most active. They are not the most massive. They are not the most spectacular. They are the ones that change the least for the longest time. This reframes the search entirely. Instead of asking where life might exist now, we must ask where life had enough uninterrupted time to emerge at all. And that leads us back to our own galaxy. Is the Milky Way simply one suitable environment among many? Or does its history place it within a rare class of galaxies that offered life the time it needed? After examining galaxies across the universe, the question inevitably turns inward. What kind of galaxy do we live in? The Milky Way is not the largest spiral galaxy. It is not the calmest. It is not the most chemically rich. Yet it occupies a curious middle ground. Our galaxy has avoided major mergers for billions of years. Its star formation rate has remained moderate rather than explosive. Its central black hole is quiet, rarely flooding the galaxy with dangerous radiation. Supernovae occur, but infrequently enough to leave long stretches of relative calm. These traits are not dramatic, but for life they are decisive. The Milky Way evolved slowly enough to enrich itself with heavy elements, yet gently enough to avoid repeated biological resets. It produced generations of stars without exhausting its gas too quickly. It preserved a stable galactic habitable zone for billions of years. Earth formed late in this history. By the time our planet emerged, the galaxy had already passed through its most violent phases. Heavy elements were abundant. Radiation levels had declined. The environment had settled into a long era of relative stability. This timing matters. Had Earth formed earlier, it may have faced frequent sterilizing events. Had it formed much later, key energy sources and materials might have been depleted. Instead, it formed during a narrow window when conditions aligned. This does not mean the Milky Way is exceptional. It means it is sufficient. Many spiral galaxies likely share similar histories. Some may be calmer, others more active, but the Milky Way belongs to a class of galaxies that offer life a rare combination of enrichment, stability, and time. From this perspective, our existence is neither miraculous nor inevitable. It is conditional. We are here because our galaxy changed slowly enough, because it avoided extremes, because it allowed complexity to accumulate instead of being erased. The Milky Way did not guarantee life. It allowed it, and that distinction carries an important implication. If our galaxy is merely one example of a suitable environment, then others like it may exist across the universe, some perhaps offering even better conditions. Galaxies where stability lasted longer, where radiation was lower, where chemical enrichment followed an even gentler path. If life arose in those places, it may have appeared earlier than on Earth. It may have evolved further, or it may have vanished long before we began to look, which leads to the final question. If some galaxies are better at creating life than others, what does that say about our place in cosmic history? To answer that, we must step beyond comparison and consider the larger implication of a universe where life is shaped not by planets alone but by the galaxies that host them. When we look across the universe through this lens, the search for life takes on a different meaning. Life is no longer just a planetary accident. It is the outcome of a long chain of cosmic conditions, each one dependent on the last. Stars must form at the right pace. Galaxies must evolve with restraint. Heavy elements must accumulate without constant destruction. And above all, time must pass without interruption. In this view, the universe is not uniformly hospitable. Some galaxies burn too fast, flooding their worlds with energy that erases complexity before it can take hold. Others grow too quiet, failing to provide the materials and renewal life needs to persist. Only a narrow class of galaxies strike the balance where creation and stability coexist. This suggests something subtle but profound. Life may not be rare because planets are rare. It may be rare because suitable galaxies are, and even within those galaxies opportunity is limited. Habitable regions shift. Windows open and close. Worlds that form too early or too late may never cross the threshold from chemistry to biology. From this perspective, Earth's story becomes both ordinary and extraordinary. Ordinary because it follows physical rules that likely apply elsewhere, or extraordinary because it unfolded within a narrow cosmic window that did not last forever. If there are galaxies better at creating life than ours, they're civilizations. If they exist, may have risen long before humanity looked up at the stars. They may have faced their own endings before our species emerged, or they may still be there evolving quietly beyond our reach and our awareness. The universe does not promise that life will appear wherever it can. It only offers chances shaped by galaxies, by time and by balance. And as we continue to search the cosmos, we may come to realize that the most important question is not whether life exists elsewhere, but where the universe gives it enough time to begin. Not all galaxies are equal. Some burn their fuel too fast, flooding space with radiation that erases complexity before it can begin. Others grow old and quiet, running out of the materials life needs to survive. Most fall somewhere in between, capable of forming stars and planets, but hostile to life over the long term. Yet among the hundreds of billions of galaxies in the observable universe, a small fraction may stand apart. Galaxies where stars form slowly and predictably, where catastrophic events are rare, where heavy elements accumulate without constant destruction, where planetary systems can remain stable for billions of uninterrupted years. These are not the brightest galaxies. They are not the most massive. They are not the ones that dominate astronomical images. They are the ones that give lifetime. If life is shaped not only by planets and stars but by the galaxies that host them, then the question becomes unavoidable. Which galaxies create the best conditions for life to begin, survive and endure? Are there galaxies more welcoming than our own? Places where biology may have appeared earlier, had more time to evolve, or reached levels of complexity far beyond anything Earth has known. Tonight we begin a different kind of search, not for life itself, but for the environments that make life possible in the first place. This is a journey across the universe's most promising neighborhoods, the galaxies that may be the most life-friendly of all. If galaxies shape the fate of life, then the universe is not a level playing field. Some galaxies offer stability only briefly. Others provide calm but too late after the materials for life are gone. A few may strike the balance where chemistry, time and stability align for billions of years. The challenge is that none of this is obvious from a distance. Through telescopes, galaxies appear as points of light, spirals of colour or faint smudges against the dark. They do not advertise their histories. They do not reveal how often stars exploded nearby, how violently they evolved, or how many times potential life was erased before it could grow. To find the most life-friendly galaxies, we must look beyond appearances. We must ask different questions. How fast does a galaxy turn gas into stars? How often does it experience violent mergers? How efficiently does it recycle the elements life depends on? And how long does it maintain regions where planets can remain stable without interruption? This turns the search into a process of elimination. Galaxies that evolve too fast are removed from consideration. Galaxies that stagnate too early are set aside. Galaxies dominated by radiation collisions or instability fall away one by one. What remains is not a single perfect candidate, but a small class of galaxies that share a rare combination of traits. They evolve slowly, they avoid extremes, they change but gently. This is not a list written in advance. It is a selection shaped by physics, history and time, and as we narrow the field, something unexpected begins to emerge. The galaxies most likely to support life are not the ones that command attention. They are not the cosmic giants or the brightest beacons in the sky. They are the quiet achievers of the universe. To understand why, we must first define what life-friendly truly means, not in human terms, but in cosmic ones. Only then can we begin to identify which galaxies belong on that short list. Before we can identify the most life-friendly galaxies, we must confront a basic problem. Life-friendly does not mean comfortable, it does not mean familiar, and it does not mean Earth-like. In a cosmic sense, life-friendly means something far more precise. A galaxy must allow complexity to emerge and survive for billions of years. That immediately rules out simple checklists. No single ingredient guarantees success. Instead, life depends on a balance of conditions that must persist across immense spans of time. The first of those conditions is pace. A galaxy that converts gas into stars too quickly burns through its resources early. Radiation surges, supernovae arrive in waves, any developing chemistry is repeatedly erased. A galaxy that forms stars too slowly faces the opposite problem. Heavy elements accumulate at a crawl. Planetary systems form late if at all. By the time stable environments exist, key energy sources may already be fading. The most life-friendly galaxies sit between these extremes. They form stars steadily, not explosively. They enrich themselves gradually without constant destruction. The second condition is stability. Life does not require a perfectly calm universe, but it does require predictability. Galaxies that experience frequent mergers, close encounters or prolonged active phases subject their planets to repeated resets. Orbits destabilize, atmospheres erode, evolution never gains momentum. In contrast, galaxies that remain relatively isolated preserve continuity. Planetary systems endure, chemical processes have time to explore complexity rather than starting over. The third condition is material richness. Life relies on elements forged inside stars and scattered by stellar death. Carbon, oxygen, nitrogen ion and radioactive elements are not optional extras. They shape atmospheres, drive geology and protect planets from radiation. Galaxies that lose their gas too early lock these elements away. Galaxies that eject material through violent winds fail to recycle it efficiently. Life-friendly galaxies must retain and redistribute their metals without overwhelming their own environments. Finally, there is time itself. Even under ideal conditions, life is slow. It requires uninterrupted eras measured in billions of years. Any galaxy that repeatedly disrupts its habitable regions eliminates the very process it might otherwise support. When these criteria are combined, a clear picture emerges. The most life-friendly galaxies are not optimized for brilliance or activity. They are optimized for endurance. They evolve slowly. They avoid extremes. They provide long windows where complexity can accumulate without being erased. With these criteria in place, the search becomes narrower and more revealing. Only certain types of galaxies consistently meet these demands. And the first place to look is not where galaxies are dramatic, but where they are quietly well behaved. Spiral galaxies are often treated as a single category. Graceful arms, rotating disks, ongoing star formation. But when it comes to life, not all spiral galaxies are created equal. Some spirals burn too fast. Their arms are crowded with massive stars. Radiation levels run high. Supernovae arrive frequently enough to threaten long-term stability. Others evolve more gently. Their star formation proceeds at a measured pace. Explosive events are spaced far apart. Planetary systems have time to settle into stable configurations. The difference lies in how a spiral galaxy manages its energy. Galaxies with tightly wound arms and rapid rotation tend to regulate star formation more effectively. Gas spreads across the disk rather than collapsing all at once. This prevents runaway bursts that flood the galaxy with radiation. In contrast, loosely organized spirals can experience prolonged periods of intense activity. While productive, these phases are biologically expensive. Mass also plays a role. Very small spiral galaxies struggle to retain heavy elements. Very massive ones often sit in crowded environments where interactions are common. The most promising candidates fall in between large enough to be chemically rich yet isolated enough to remain undisturbed. Isolation, in fact, is critical. Spiral galaxies that drift far from clusters avoid frequent mergers. Their disks remain intact for billions of years. Their galactic habitable zones persist rather than shifting violently over time. These galaxies quietly accumulate the ingredients life needs without repeatedly erasing progress. The Milky Way belongs to this group, but it may not be the best example. Other spirals show even calmer histories, lower supernova rates, slower star formations, wider regions of long-term stability. In these galaxies, habitable zones are not narrow rings, but broad swaths of space where planetary systems can endure for immense spans of time. From a biological perspective, this matters more than beauty or size. A spiral galaxy done right does not maximize production. It maximizes continuity, and continuity is the currency life depends on. But spiral structure alone is not enough. To identify the most life-friendly galaxies of all, we must look for systems that take everything. Spirals do well and refine it even further. Galaxies that are large, calm, isolated, and patient. Quiet giants. Some spiral galaxies take balance to another level. They are large, massive systems, rich in gas and heavy elements. Yet remarkably calm, these galaxies rotate slowly. Their disks are wide and well-ordered. Star formation unfolds at a steady, almost restrained pace. They are not in a hurry. In these quiet giants, catastrophic events are rare. Supernovae occur but are spread across vast volumes of space. Radiation levels remain moderate. Planetary systems enjoy long stretches of uninterrupted stability. From the perspective of life, these galaxies offer something extraordinary. Time without pressure. Their size allows them to retain heavy elements efficiently. Gas is recycled rather than expelled. Successive generations of stars form with increasing chemical richness. At the same time, their isolation shields them from disruption. Far from dense clusters, they avoid frequent mergers and close encounters. Their disks remain intact. Their habitable zones persist rather than shifting violently. This combination, mass without chaos, is rare. Many large galaxies grow through repeated collisions. They become distorted, heated, and unstable. But quiet giants appear to have evolved, gently assembling most of their mass early and then changing little afterward. As a result, their galactic habitable zones can be unusually broad. Instead of narrow rings, these galaxies may host extended regions where radiation levels, star density, and chemical richness remain favorable over billions of years. In such environments, life does not need to race against catastrophe. Evolution can proceed slowly, exploring complexity without constant resets. Compared to these systems, the Milky Way looks respectable but not exceptional. Our galaxy is moderately calm but not perfectly so. Its star formation has fluctuated. Its past includes minor mergers and bursts of activity. Quiet giants may offer even longer windows of stability. Galaxies where life could have emerged earlier. where evolution may have had more time to experiment, where complexity might have reached levels beyond what Earth has known. But identifying these galaxies raises a natural question. If some spirals are better than others, how does our nearest large neighbour compare? Is the Andromeda Galaxy a better cradle for life than the Milky Way, or is its apparent calm hiding a more complicated history? At first glance, Andromeda appears to have an advantage. It is larger than the Milky Way, it contains more stars, its disk is broader, and its overall star formation rate is slower and more subdued. On paper, these traits seem ideal. Slower star formation means fewer massive stars. Fewer massive stars mean fewer supernovae. Lower radiation levels translate into longer periods of planetary stability. In several respects, Andromeda looks calmer than our own galaxy. Its galactic habitable zone may be wider. Its chemical enrichment is comparable, if not slightly higher. Some regions may have enjoyed long uninterrupted eras where complex chemistry could persist. If habitability were judged only by present conditions, Andromeda might appear more life-friendly than the Milky Way. But galaxies carry histories, not snapshots, and Andromeda's past tells a more complicated story. Evidence suggests that Andromeda experienced significant mergers earlier in its evolution. Its disk shows signs of past disruption. Waves of star formation ripple through its structure, likely triggered by ancient collisions. These events enrich the galaxy, but at a cost. Each merger reshaped orbits, destabilized planetary systems, and flooded regions with radiation. Any early life may have faced repeated resets before conditions finally settled. Even more important is Andromeda's future. Andromeda and the Milky Way are on a collision course. In several billion years, the two galaxies will merge, transforming both into a new system entirely. From a biological perspective, this matters. A galaxy may be life-friendly now, yet hostile across the full span of time life requires. If Andromeda offered wider habitable zones, it may also have offered them for shorter windows. Its calm periods may have been punctuated by violence more often than ours. This highlights a crucial distinction. Life-friendliness is not just about how good conditions are. It is about how long those conditions last. A galaxy that is slightly less ideal but stable for longer may ultimately be a better cradle for life than one that's briefly perfect. The Milky Way, for all its imperfections, has enjoyed a remarkably long period without major disruption. That continuity may outweigh Andromeda's advantages. Andromeda may be a strong contender, but is not a clear winner. To find galaxies that outperform both, we must look beyond familiar spirals towards systems that evolve even more quietly. Galaxies that emit little light, attract little attention, and rarely make headlines. Low-surface brightness galaxies. Some of the most promising galaxies for life are also the hardest to see. Low-surface brightness galaxies do not shine brightly against the cosmic background. Their stars are spread thin. Their disks are diffuse. From a distance, they almost fade into darkness. For decades, astronomers overlooked them. They appeared unproductive, underdeveloped. Too quiet to matter. But quiet in this context may be exactly the point. Low-surface brightness galaxies form stars at extremely slow rates. Massive stars are rare. Supernovae occur infrequently. Radiation levels remain low and stable over immense spans of time. From a biological perspective, these conditions are unusually gentle. Planetary systems in such galaxies are unlikely to experience repeated sterilizing events. Atmospheres may persist for billions of years. Evolution, if it begins, is rarely forced to start over. The primary concern is chemistry. Low-surface brightness galaxies tend to be metal-poor. Heavy elements accumulate slowly. Rocky planets may be fewer, and those that form may lack the internal energy needed to remain geologically active. Yet this limitation is not absolute. Even a small number of supernovae can enrich local regions enough to form complex planets. Over billions of years, slow enrichment can still reach meaningful levels, and because these galaxies retain their gas, that material is recycled rather than lost. Another factor works in their favour. Low-surface brightness galaxies are often isolated. They drift through underdense regions of the cosmic web, far from clusters and frequent interactions. Their evolution is not interrupted by mergers or tidal disruption. This isolation preserves stability at every scale. Star orbits remain undisturbed. Planetary systems persist. Habitable regions shift slowly, if at all. Life in such galaxies may be rare, but rarity is not the same as improbability. If life appears in these environments, it may enjoy longer uninterrupted histories than in more active systems. Complexity may grow slowly but steadily. These galaxies challenge a deeply rooted assumption that brightness and activity are signs of potential, that productivity equals habitability. In reality, the most life-friendly environments may be those that change the least, galaxies that barely draw attention, galaxies that evolve patiently over cosmic time. Yet even the quietest systems are shaped by their surroundings. To find the most enduring cradles of life, we must look not only at galaxies themselves, but at where they live in the cosmic landscape. That means turning to galaxies with almost no neighbours at all. In the universe, location matters, not just within a galaxy, but among galaxies. Some galaxies live crowded lives. They orbit within dense clusters surrounded by thousands of neighbours. Gravity pulls constantly. Gas is stripped away. Radiation from nearby systems fills intergalactic space. Others live in near solitude. Isolated galaxies drift through underdense regions of the cosmic web. They experience few close encounters. They avoid major mergers. Their evolution unfolds slowly, almost uninterrupted. From the perspective of life, this isolation is powerful. Galactic interactions are among the most disruptive events in the universe. They trigger bursts of star formation. They awaken central black holes. They reshape disks, destabilize orbits, and flood space with radiation. A galaxy that avoids these encounters preserves continuity. Its stars follow stable paths for billions of years. Planetary systems remain gravitationally undisturbed. Habitable regions shift gradually rather than violently. This stability compounds over time. Chemical enrichment proceeds steadily. Radiation environments remain predictable. Evolution, if it begins, is rarely forced to restart. Isolated galaxies are often spiral or low-surface brightness systems, but not exclusively. What unites them is not shape, but history. They assembled early. They change little afterward. In these galaxies, the timeline of habitability can stretch unusually long. Instead of brief windows, life may have billions of uninterrupted years to emerge and adapt. There is, however, a trade-off. Isolation can limit growth. Fewer mergers mean fewer sudden injections of gas and metals. Star formation remains slow, but for life slow is not a weakness. Complexity does not need abundance. It needs persistence. A single habitable world left undisturbed for billions of years may achieve more than countless worlds repeatedly reset by catastrophe. This reframes how we think about cosmic neighborhoods. Galaxy clusters may be spectacular. They are not necessarily friendly. The quiet outskirts of the universe, cosmic voids and filaments far from congestion, may host galaxies that quietly outperform their crowded counterparts. And yet isolation alone does not guarantee success. Some galaxies are isolated and still hostile, dominated by intense internal activity. Others are calm inside but shaped by violent pasts. To complete the selection, we must eliminate entire classes of galaxies that fail regardless of isolation or size. Galaxies whose internal engines overwhelm any chance for long-term stability. Some galaxies fail the test not because they lack resources, but because they have too much of them. Too much energy, too much radiation, too much change. At first glance, these galaxies appear promising. They are bright. They are productive. They forge heavy elements at astonishing rates. But life does not thrive in excess. Starburst galaxies are the clearest example. In these systems, gas collapses, rapidly igniting waves of star formation. Massive stars dominate. Supernovae erupt in quick succession. Radiation saturates entire regions of space. Any planet attempting to nurture life in such an environment faces relentless disruption. Atmospheres erode. Surface chemistry is sterilized. Evolution never gains momentum. Even if life begins, it rarely survives long enough to grow complex. Galaxies dominated by active galactic nuclei present a similar problem. When a central black hole enters an active phase, it floods its surroundings with high-energy radiation. Jets and winds reshape the galaxy's interior. Habitability zones collapse or shift unpredictably. These phases may last tens or hundreds of millions of years, long enough to erase progress across vast regions. Frequent mergers compound the damage. Each collision compresses gas, triggers starbursts, and destabilizes planetary systems. Orbits shift, stars are displaced, entire habitable regions are rearranged or destroyed. Some galaxies appear calm now, but their histories betray them. They carry scars of repeated interactions. Their stability is recent. Their windows for life are narrow. From a biological perspective, these galaxies are unreliable. Life cannot plan around catastrophe. It cannot adapt fast enough to constant upheaval. The most life-friendly galaxies are not those that maximize energy output. They are those that minimize biological resets. This process of elimination leaves us with a narrower, quieter class of systems. Galaxies that change slowly. Galaxies that avoid extremes. Galaxies whose histories are defined more by patience than by drama. Yet even among these survivors, not all are equal. One final factor outweighs every other. Timing. A galaxy can have the right structure, the right chemistry, the right level of stability, and still fail. Because life is not only about where conditions exist, it is about when they exist. Galaxies evolve. They pass through phases, violent beginnings, calmer middle ages, and eventual decline. At each stage, their ability to support life changes. Early in a galaxy's history, heavy elements are scarce. Planets form poorly. Radiation levels are high. Supernovae are frequent. Life may try to begin, but the environment is unforgiving. Later, as stars enrich the galaxy with metals, conditions improve. Rocky planets become common. Radiation levels fall. Habitable regions expand. This is often the golden era for life, but it does not last forever. As star formation slows, energy sources fade. Geological activity weakens. Magnetic fields decline. Atmospheres erode over immense spans of time. A galaxy that becomes too quiet too early may miss its window entirely. This means life-friendliness is not a permanent property. It is a phase. A galaxy may be hostile for billions of years, then supportive for a brief window and hostile again. Another may offer moderate conditions for an exceptionally long time. From a biological perspective, the second galaxy is far more promising. Long windows matter more than perfect conditions. This reframes the search. We are not looking for galaxies that are ideal right now. We are looking for galaxies that remain suitable long enough for complexity to emerge. Some galaxies may have been better than the Milky Way, but only briefly. Others may never have reached that threshold at all. It is also possible that many of the best environments existed long before Earth formed. Life may have appeared elsewhere billions of years earlier. It may have risen, adapted, and vanished before our planet even cooled. If that is true, then the universe's most life-friendly galaxies may no longer host life today. They may be ancient cradles whose opportunity has passed. This introduces a humbling possibility. We may be late to the cosmic story, not because life is rare, but because the best conditions occurred earlier in places we're only now beginning to observe. To understand what remains today, we must shift our focus again, away from timing alone and toward visibility, because the galaxies most friendly to life may not be the ones we notice most easily. When we imagine the best places for life in the universe, our instincts mislead us. We are drawn to brilliance, to massive galaxies blazing with stars, to dramatic spirals captured in breathtaking detail, but visibility is not the same as suitability. The galaxies most favourable to life may be the ones that escape attention entirely. Faint galaxies, diffuse systems, galaxies that do not dominate surveys or headlines. These galaxies form stars slowly. They emit less radiation. They experience fewer violent events. They do not announce themselves. From a distance, they look unremarkable, but from the perspective of life, they may be extraordinary. Low radiation environments preserve atmospheres. Sparse stellar neighborhoods reduce the risk of nearby supernovae. Long-lived stars provide steady energy over immense spans of time. In such galaxies, nothing happens quickly, and that may be their greatest advantage. Life does not need spectacle, it needs patience. The universe's brightest galaxies burn through their potential early. They exhaust gas. They reshape themselves through collisions. They shorten the windows where stability exists. The quiet galaxies endure. They change slowly. They retain gas. They preserve habitable regions for billions of years. These systems may host fewer planets overall, but the planets that do exist may enjoy far longer uninterrupted histories. From a biological perspective, one stable world is worth more than thousands repeatedly reset by catastrophe. This forces us to reconsider how we search. Astronomical surveys are biased toward brightness, toward activity, toward spectacle. But life may prefer anonymity. If intelligent civilizations arise in such galaxies, they may be rare, not because life is unlikely, but because their homes are difficult to detect. They may not broadcast their presence through brilliant starbursts or luminous cores. They may exist quietly evolving under steady stars in faint galaxies far from cosmic crowds. The universe may be filled with places where life could thrive, places we overlook simply because they do not stand out. And that leads to one final unsettling question. If the most life-friendly galaxies are faint, ancient, and quiet, then where does that leave us? Once we accept that some galaxies are better at creating life than others, a deeper question emerges. Where do we stand in time? If the most life-friendly galaxies are those that evolved calmly and early, then life elsewhere may not be something that appears alongside us. It may have appeared long before us. Many of the quietest, most stable galaxies formed early in the universe. They assembled, their mass quickly avoided major disruptions, and then changed very little for billions of years. In those environments, the conditions for life may have arrived sooner than they did in the Milky Way. Heavy elements accumulated earlier. Radiation declined earlier. Long windows of stability opened while our galaxy was still evolving. If life began there, it may have had an enormous head start. Civilizations could have risen, adapted, and perhaps vanished long before Earth formed its first oceans. Others may have reached levels of complexity we cannot yet imagine, or they may have chosen paths that left no obvious traces. This challenges a comforting assumption that we are near the beginning of the cosmic story. Instead, we may be arriving late, in a universe where many of the best opportunities have already passed. But there is another possibility. Perhaps life-friendly conditions are not clustered early in time. Perhaps they peak during long quiet eras like the one we inhabit now. Perhaps the universe needed billions of years to mature before life could reliably take hold. If so, then humanity may be closer to the beginning than it appears. We may be among the early participants in a much longer cosmic process. The truth may lie between these extremes. Life may arise sporadically across time, flaring briefly in some galaxies and enduring quietly in others. The universe may not host a single biological era, but many each shaped by the rise and fall of suitable galaxies. In that case, the question is not simply where life exists, it is when it exists. And whether we are early, late, or precisely on time depends on how long the universe continues to produce galaxies capable of supporting complexity. To answer that, we must step back one final time, beyond rankings, beyond candidates, beyond our own galaxy, and ask what this all means for the search ahead. As our picture of the universe grows clearer, one conclusion stands out. Life is not distributed at random. It follows patterns shaped by physics, history, and time. It favors galaxies that evolve, slowly avoid extremes, and preserve stability across billions of years. The universe does not offer life equal opportunity. It offers windows. Some galaxies open those windows early and close them quickly. Others keep them open quietly for longer than we might expect. Many never open them at all. This means the search for life cannot be limited to planets or stars. It must extend to the galaxies that host them, and to the cosmic eras in which those galaxies exist. The most life-friendly galaxies may not be the most visible today. They may be faint, ancient, or already past their biological prime. If that is true, then the universe may have hosted life long before Earth formed. Not everywhere, but in a small number of carefully balanced environments. Our own galaxy may be one of many that briefly met those conditions, or it may represent a second wave appearing after earlier opportunities faded. Either way, the implication is profound. Life in the universe may be widespread across time, even if it is sparse across space. And that changes what it means to search. We are not just looking for neighbours, we are looking for survivors of long cosmic histories, civilizations that arose in galaxies patient enough to give them time, worlds that endured without interruption, stories that unfolded quietly beyond our awareness. The next question then is not simply where life exists now, it is where life appeared first, and whether those earliest cradles of life still exist or have already gone dark. If some galaxies are better at creating life than others, then one final assumption begins to crack. That life in the universe began roughly when it began here. Earth formed about 4.5 billion years ago. Life appeared soon after. For a long time, that timeline felt natural, almost inevitable. But the universe is far older. By the time Earth formed, galaxies had already existed for billions of years. Stars had lived and died. Heavy elements had been forged, scattered, and recycled again and again. Entire galactic environments had already passed through their most violent phases, which raises a quiet but unsettling possibility. Life may not have begun on Earth early. It may have begun late. In other galaxies, under calmer conditions, with more time and fewer interruptions, the chemistry of life may have crossed the threshold long before our planet even existed. Worlds may have stabilized while Earth was still molten. Oceans may have formed while our sun was still assembling. Evolution may have unfolded slowly and patiently across billions of uninterrupted years, long before the Milky Way became a suitable home. If that is true, then the universe's first living worlds were not waiting for us. They were already ancient. Tonight we step even further back in time, beyond Earth, beyond the Milky Way, beyond the era we call familiar, to explore where life might have emerged long before our planet ever formed, and what those earliest cradles of life reveal about our place in the cosmic story. When Earth formed, the universe was already old. Galaxies had been assembling for billions of years. Stars had lived full lives and died violent deaths. Heavy elements had been forged, scattered, and recycled across vast regions of space. By the time our planet took shape, the universe was no longer young. It was experienced. This matters because the early universe was not immediately friendly to life. In its first few 100 million years, stars formed rapidly and died young. Radiation levels were intense. Supernovae were frequent. Heavy elements were scarce. Planets, if they formed at all, were primitive. Rocky worlds were rare. Stable environments were difficult to maintain. Life may have been possible in principle, but unlikely to persist. As time passed, conditions changed. Successive generations of stars enriched galaxies with carbon, oxygen, nitrogen, and iron. Radiation levels gradually declined. Star formation slowed. Galaxies settled into more stable configurations. This transition marked a turning point. For the first time, the universe began to offer environments where complexity could endure rather than be erased. In some galaxies, this shift happened early. They formed stars, efficiently enriched themselves quickly, and then calmed down. They avoided frequent mergers. They preserved stability for billions of years. In others, including the Milky Way, the process took longer. Our galaxy spent much of its early history in a more turbulent state. Star formation was higher, supernovae were more common, habitable regions were narrower and less stable. Earth did not appear until these conditions improved. But elsewhere the clock may have started sooner. In galaxies that matured early and evolved gently, planets could have formed under calmer skies long before Earth existed. Oceans could have stabilized. Chemistry could have explored complexity without constant interruption. If life emerged in those environments, it may have had a head start measured not in millions but in billions of years. This does not mean life was widespread, only that the opportunity existed earlier than we once assumed. To understand where the opportunity first appeared, we must examine which galaxies reached biological maturity before our own, and that means looking back to a very different universe, one where the Milky Way was still becoming suitable. While other galaxies may have already crossed the threshold, not every galaxy took the same path through cosmic history. Some assembled quickly, burning through their most violent phases early. Others grew slowly, remaining unstable for billions of years before finally settling down. The difference mattered. In the early universe, many galaxies were chaotic places. Gas collapsed rapidly. Massive stars formed in dense clusters. Supernovae erupted in frequent waves, flooding space with radiation. But a small number of galaxies evolved differently. They formed stars efficiently at first, enriching themselves with heavy elements, then slowed down before constant violence could take hold. These were the universe's first calm galaxies. Their early growth provided the materials life requires. Their later restraint preserved stability. And together these traits created environments unlike anything the young Milky Way could yet offer. In these galaxies, star formation transitioned from explosive to measured. Radiation levels declined earlier. Habitable regions widened sooner. Planets forming in these systems faced fewer catastrophic resets. Atmospheres had time to accumulate and persist. Chemistry could explore complexity without being repeatedly erased. This early calm did not happen everywhere. Galaxies in dense regions continued to collide and merge. Others remained chemically poor, forming stars too slowly to support complex planets. But isolated systems, those drifting away from crowded cosmic neighborhoods, were different. Their histories were quieter, their evolution gentler. By the time Earth's future building blocks were still scattered across interstellar space, some of these galaxies may already have hosted stable, long-lived worlds. If life depends on patience more than speed, then these early calm galaxies may have offered the universe its first real chance. Not everywhere, not often, but earlier than we once believed. To understand what kind of life might emerge in such ancient environments, we must examine the worlds themselves. Worlds that formed under skies calmer than ours, around stars older than our sun, in galaxies that had already learned how to slow down. The earliest opportunities for life did not belong to stars like our sun. They belonged to stars that lived longer. In the early universe, many massive stars burned brightly and died quickly. They flooded space with radiation, then vanished in violent explosions. These stars enriched galaxies, but they were poor companions for life. The worlds that mattered formed around quieter stars. Low-mass stars burned slowly. They change little over time. Some can shine steadily for tens or even hundreds of billions of years. In the first calm galaxies, these stars became the anchors of stability. Planets forming around them faced fewer sudden disruptions. Radiation environments softened earlier, and once atmospheres formed, they were less likely to be stripped away. These ancient stars offered something rare in the early universe: continuity. Around them, worlds could cool gradually, oceans could condense, chemistry could proceed without constant interruption. Some of these planets may have formed billions of years before Earth existed. They would have orbited stars already old when our sun was still a collapsing cloud of gas. Their skies would have aged slowly. Their climates may have remained stable for unimaginable spans of time. But age alone is not enough. Early planets faced a challenge. The universe had not yet reached its peak chemical richness. Heavy elements were present but not abundant. Planetary systems formed leaner, simpler, and more fragile. Yet even modest enrichment can be sufficient. Life does not require excess. It requires consistency. A planet with fewer resources but uninterrupted stability may outperform a richer world constantly reset by catastrophe. In these ancient systems, evolution may have taken a different path. Slower, more constrained, but persistent. Life may have emerged, gradually refining itself over billions of years rather than racing against extinction. If such worlds existed, they would represent the universe's first experiments with biology. Not short-lived sparks, but slow-burning processes unfolding across deep cosmic time. And if life gained a head start there, the implications are profound. Because the earliest living worlds may not resemble Earth at all. They may belong to stars older than our sun, galaxies quieter than our own, and eras of the universe we're only beginning to understand. To follow that possibility further, we must ask a difficult question. What kind of life could survive for billions of years longer than life on Earth has existed? On Earth, life has existed for nearly 4 billion years. That may sound like an eternity. In cosmic terms, it is not. Our planet spent much of its early history recovering from impacts, volcanic upheaval, and unstable conditions. Complex life appeared late. Technological intelligence arrived only moments ago, measured against the age of the universe. But in other galaxies, the clock may have started much earlier. If life emerged on ancient worlds billions of years before Earth formed evolution, they would not simply be older, it would be fundamentally different. Given enough time, evolution does not just refine complexity, it explores entirely new pathways. On Earth, mass extinctions repeatedly reset progress. Asteroid impacts, climate shifts, and geological upheavals erased dominant species and reshaped ecosystems. Each reset forced life to rebuild rather than continue uninterrupted. In calmer galaxies on calmer worlds, those resets may have been fewer. A planet that avoids global catastrophes for billions of years allows evolution to accumulate rather than restart. Biological innovations build upon earlier ones. Complexity compounds. Over such timescales, life could move far beyond microbial beginnings. Not quickly, but steadily. If intelligence emerged early in these environments, it would not merely be ahead of us by time, it would be ahead by opportunity. More time to adapt, more time to diversify, more time to respond to challenges without extinction. Such life may not resemble anything familiar. It may rely on biochemistry optimized for ancient metal-poor environments. It may favor efficiency over abundance, stability over speed. Civilizations, if they arose, would have faced a universe very different from ours. Stars would have been closer together, the cosmic background warmer, galaxies younger and less structured. Over billions of years, those conditions would change slowly, giving such civilizations time to adjust rather than collapse. But longevity brings its own challenges. Even the calmest galaxies evolve. Energy sources fade, stars age, planets cool. A billion-year head start does not guarantee survival forever. Some ancient life may have reached peaks long ago only to decline as conditions shifted. Others may have adapted, continuously reshaping themselves to persist through cosmic change. If such life exists or once existed, it raises a quiet, unsettling thought. We may not be searching for contemporaries. We may be searching for relics, traces of life that had already lived through epochs of cosmic history before Earth ever began its story. To understand where such ancient life might still survive, we must identify the environments that change the least over the longest time. The galaxies that preserve continuity not just for billions, but for tens of billions of years. If life emerged early in the universe, its survival would depend on one factor above all others: endurance. Not just the ability to begin, but the ability to persist as the universe changes. The longest-lived habitable environments are not defined by abundance or activity. They are defined by restraint. They exist where stars burn slowly, where radiation remains low, where catastrophic events are rare enough to be counted rather than expected. In these environments, time stretches. Low-mass stars play a central role. Red and orange stars evolve far more slowly than stars like our Sun. Some can shine steadily for tens of billions of years. Their energy output changes gradually, giving surrounding worlds time to adapt rather than collapse. Planets orbiting these stars may experience climates that shift slowly, predictably, and over immense spans of time. If atmospheres form and survive, they may endure longer than Earth's ever will. But stellar longevity alone is not enough. The galaxy itself must cooperate. The longest-lived habitable environments are found in galaxies that change little after their early evolution. Galaxies that avoid major mergers. Galaxies that do not awaken their central black holes repeatedly. Galaxies that settle into quiet, stable configurations and remain there. In such systems, planetary orbits remain undisturbed for billions of years. Radiation backgrounds remain low. Habitable zones shift slowly, if at all. These conditions allow life to do something rare. They allow it to persist without interruption across deep cosmic time. In these environments, evolution does not race against extinction. It proceeds cautiously, conserving what works and refining what does not. If intelligence arises under such conditions, it may do so gradually, not driven by rapid change or frequent catastrophe, but shaped by patience. These may be the universe's most enduring biological laboratories, not places where life begins easily, but places where life once begun refuses to disappear. And if such environments exist, they may still exist today, long after early galaxies faded, long after violent eras passed, long after the universe learned how to slow down, which raises a final unsettling possibility. The oldest living worlds in the universe may not be ancient ruins. They may be ongoing stories unfolding quietly under dim stars, in galaxies that rarely change, far from the places we usually look. To recognize them, we must ask one last question. not where life could begin earliest, but where it could last the longest. If life began long before Earth, the question is no longer purely historical, it becomes immediate. Are any of those ancient life-friendly environments still out there today? The universe does not erase its past completely. Galaxies that evolve gently tend to persist. Those that avoided collisions often remain intact. Those that learned how to slow down rarely accelerate again. This means some of the earliest calm galaxies may still exist, not as relics frozen in time, but as systems that continued evolving quietly while the rest of the universe changed around them. Astronomers already know where to look: isolated galaxies, low surface brightness systems, diffuse spirals far from clusters, galaxies that show little evidence of recent mergers or violent activity. These galaxies often appear uneventful. Their stars are old, their disks are thin, their light is faint, but beneath that simplicity lies continuity. Some have likely maintained stable conditions for 10 billion years or more. Their star formation slowed early and never reignited dramatically. Their radiation environments softened long ago and remain that way. In such galaxies, habitable zones may have existed for longer than the entire age of complex life on Earth. Planets orbiting long-lived stars in these systems could have hosted life while dinosaurs still lay billions of years in the future. They could have experienced uninterrupted evolution across spans of time we struggle to imagine. If intelligence arose there, it would not be ancient by accident. It would be ancient by design. Yet these galaxies challenge our methods. They are faint. They are hard to survey. They do not dominate astronomical catalogues. Our telescopes are biased toward brightness and activity. We see what shines, not what endures. This means the most ancient life-friendly galaxies may be underrepresented in our data, not because they are rare, but because they are subtle. Quiet does not mean empty. Calm does not mean lifeless. If life survives best where disruption is minimal, then the oldest living worlds may exist in places we have barely examined. And that realization forces us to reconsider something fundamental. The search for life may not be about finding the newest habitable worlds. It may be about finding the oldest survivors. To do that, we must ask not just where to look, but how to look, and whether our assumptions are blinding us to the most important environments of all. Searching for ancient life in the universe is not just a technical challenge. It is a conceptual one. Modern astronomy is built to detect what is bright, active, and changing. We excel at finding exploding stars, energetic galaxies, and violent events. Our instruments are tuned to spectacle. Ancient life, however, may leave no spectacle behind. Galaxies that have remained calm for billions of years do not glow dramatically. Their stars are old and faint. Their radiation is subdued. Their activity levels barely register against the cosmic background. To our telescopes, these systems can look unremarkable or even empty. This creates a profound observational bias. We search for life where conditions appear exciting. We prioritize regions rich in energy and emotion. But life may prefer environments that do the opposite. Environments that change slowly, that avoid extremes, that offer continuity rather than stimulation. Even when we search for biosignatures, our expectations are shaped by Earth. We look for oxygen-rich atmospheres, for rapid chemical disequilibrium, for signs of ongoing biological activity. But ancient life may not advertise itself so clearly. After billions of years, ecosystems may stabilize. Metabolisms may become efficient recycling resources with minimal waste. Atmospheric signatures may weaken rather than intensify. A planet hosting long-lived life could appear deceptively quiet. There is also the problem of distance and time. The light we receive from distant galaxies is ancient. We are not seeing them as they are now, but as they were billions of years ago. Any life that once existed there may have already changed or disappeared by the time its light reaches us. This makes the search inherently indirect. We are not looking for life itself. We are looking for environments that once allowed life to endure. That requires a shift in strategy. Instead of asking where life is most likely to appear today, we must ask where it was most likely to persist for the longest time. This means prioritizing galaxies with calm histories, stars with long lifespans, planets with stable orbits and ancient atmospheres. It also means accepting uncertainty. Ancient life may not leave clear signatures. It may not broadcast its presence. It may never be detectable directly. Yet its absence from our data does not mean it never existed. The universe may be filled with stories that ended quietly, and recognizing that possibility reshapes the search itself. We are not explorers looking for neighbors waving back. We are archaeologists of cosmic history searching for traces of long-ended processes. To complete this journey, we must confront what all of this implies for us, not just for where life began, but for how rare or common our moment in cosmic time truly is. For decades, one question has lingered over modern astronomy: if the universe is so vast, and life seems possible in so many places, why does it appear so quiet? This question is often framed spatially. Where is everyone? But what if the silence is not about distance, but about timing? If life emerged early in the universe and galaxies calmer and older than our own, then intelligence may not be synchronized with us. Civilizations could have risen when the universe was younger, when stars were closer together, when galaxies were still settling into stable forms. They may have existed billions of years before Earth formed. And over such timescales, disappearance becomes inevitable. Stars evolve, energy sources fade, planets cool, galaxies slowly change. Even the most advanced civilizations would face limits imposed by physics and time. If intelligence emerged early, it may also have ended early, not through catastrophe, but through exhaustion, through adaptation into forms that no longer broadcast their presence, or through gradual decline as environments change beyond what technology could compensate for. In this view, the universe's silence is not evidence of emptiness. It may be evidence of age. We may be listening after the loudest moments have already passed. Earth formed late in a universe that had already experimented with life for billions of years. Our emergence may coincide not with the beginning of cosmic biology, but with its long, quiet aftermath. This reframes the search for extraterrestrial intelligence. We are not waiting for neighbors to speak. We are listening for echoes of processes that unfolded long before we were here, echoes that may never reach us clearly, if at all. If we are latecomers, then our task changes. We are not explorers arriving at a crowded frontier. We are historians trying to reconstruct events that left few surviving traces. And that realization carries a final, sobering implication. If life arose early and often, but rarely lasted, then our moment may be both ordinary and precious. Ordinary because biology follows physical rules. Precious because continuity is rare. Which leads to the final reflection. The universe may not be silent because life is rare. It may be silent because life is old. Long before Earth cooled, long before oceans formed on our planet, the universe may have already tested biology in other places, in galaxies that matured early, around stars that burned slowly, on worlds that enjoyed billions of uninterrupted years. Those experiments may have succeeded. For a time, life may have emerged adapted, diversified, and even grown intelligent. Not everywhere, not often, but earlier than we once imagined. And then, as conditions changed, those stories may have ended. Not with explosions or cosmic drama, but with gradual fading. Stars aged, energy declined, planets cooled, habitability slipped away slowly and quietly. If that is how life unfolded elsewhere, then the universe is not empty. It is experienced. It has already explored many of the paths we are just beginning to walk. Our own moment may be part of a later chapter, one that appears after earlier opportunities passed, in a galaxy that learned how to remain calm just long enough. This does not diminish our place in the cosmos. It deepens it. We are not anomalies in a lifeless universe. We are participants in a long, patient experiment, one that may have begun billions of years before us, and may continue long after. The search for life, then, is not only about discovery. It is about perspective, about understanding that biology is shaped by time as much as by space, that survival matters more than beginnings, that continuity is rarer than creation, and perhaps someday when we finally detect a distant biosignature, or uncover an ancient chemical trace on a long-dead world, we will realize something profound, that the universe did not wait for us to begin living. It simply gave life many chances, and we are one of them. When we search for life beyond Earth, we often imagine a single question with a single answer. Is life rare or common? But the universe may not work that way. Life may not be a yes or no phenomenon. It may be a process the universe has attempted repeatedly, under different conditions, in different places, at different times. Earth may not be the universe's first success. It may not even be its most ambitious attempt. Across cosmic history, galaxies have formed and faded, stars have ignited and died, planets have appeared, evolved and vanished. Each of these moments carried the same possibility, that chemistry might cross a threshold, that matter might organize itself, that life might begin. And in some cases it may have, but beginnings are easy. Survival is not. The universe is old enough to have tried life many times, and unforgiving enough to have erased most of those attempts. Worlds may have lived and died quietly. Biologies may have risen and fallen without leaving signals strong enough to cross cosmic distances. Entire evolutionary stories may have unfolded, then disappeared long before Earth ever formed. If that is true, then the universe is not silent because life failed. It is silent because life is fragile across deep time. Tonight we explore a different possibility, that life is not rare in space, but rare in duration, that the universe may have tried life again and again, and that we are witnessing one of the few attempts still in progress. The universe does not run a single trial. It runs processes. Over nearly 14 billion years, the same ingredients have been mixed again and again. Hydrogen and helium collapsed into stars. Stars forged heavier elements. Those elements assembled into planets, oceans and atmospheres. Each cycle created a new opportunity. From this perspective, life is not a miracle event. It is a threshold, one the universe may cross whenever conditions align. Chemistry does not care whether it has tried before. Physics does not remember past failures. Every suitable environment is a fresh experiment. And the universe has provided many. Planets formed early and often. Galaxies matured at different rates. Some environments became calm quickly. Others remained turbulent for eons. Each time stability emerged, the same question was asked without intent or awareness. Can complexity persist here? In some cases, the answer may have been yes. Life could have begun as simple chemistry, organizing itself slowly under steady conditions. Given enough time, it may have diversified, adapted, explored pathways that no longer exist today. But the universe is not designed to protect experiments once they begin. Stars evolve, galaxies collide. Radiation rises and falls, energy sources fade. An experiment that succeeds briefly can still fail in the long run. This suggests a different way of thinking about cosmic life, not as a single emergence waiting to be discovered, but as a sequence of attempts, some short-lived, some longer, most ultimately erased. The universe may have tried life in early galaxies that later grew hostile. It may have tried life on planets that lost their atmospheres. It may have tried life around stars that burned too fast or faded too slowly. Each attempt followed the same rules. Begin where conditions allow, persist while conditions remain, and when conditions change, beyond recovery. From this view, Earth is not special because life appeared here. It is notable because life has lasted here. For billions of years, our planet avoided complete resets. Our star remained stable. Our galaxy stayed calm enough. Not perfect, just sufficient. This reframes the search entirely. We are not asking whether the universe is capable of producing life. We are asking how often life survives long enough to matter. And to answer that, we must examine the forces that repeatedly erase these experiments. Forces that operate quietly, relentlessly, and on timescales far longer than any civilization. If the universe has tried life many times, then failure must be part of the pattern. Not dramatic failure, not sudden annihilation, but gradual loss. Most environments that allow life to begin do not remain stable forever. Stars brighten as they age. Radiation levels shift. Habitable zones migrate outward. Worlds that were once temperate slowly overheat or freeze. On shorter timescales, galaxies intervene. A nearby supernova can strip atmospheres. A passing star can destabilize planetary orbits. A minor galactic interaction can trigger waves of radiation that linger for millions of years. None of these events are rare in cosmic history. They are expected. Even planets that begin under ideal conditions face long odds. Magnetic fields weaken. Geological activity slows. Carbon cycles break down. Without internal renewal, climates drift beyond recovery. Life does not need perfection, but it does need continuity. And continuity is fragile. In many early galaxies, conditions improved quickly but did not last. Chemical enrichment arrived early, but star formation remained intense. Radiation declined briefly, then surged again. These environments may have allowed life to begin, only to erase it before complexity could accumulate. In other cases, life may have endured longer but still lost the race against time. A planet may host biology for hundreds of millions of years, yet never experience the long calm required for intelligence to emerge. From a cosmic perspective, these are failed attempts not because life could not begin, but because it could not persist. This reframes extinction. Extinction is not an exception in the universe. It is the default outcome. The longer a biological experiment runs, the more opportunities there are for conditions to drift beyond tolerance. Earth's history illustrates this clearly. Even here, mass extinctions nearly erased complexity multiple times. Only luck timing and geological resilience prevented complete collapse. Most worlds may not be so fortunate. They may lose their atmospheres quietly. Their oceans may evaporate slowly. Their stars may change just enough to make recovery impossible. No catastrophe is required, only time. If life is a repeated experiment, then the universe has likely ended far more experiments than it has sustained, which makes the surviving ones like Earth statistical outliers rather than typical outcomes. To understand why some experiments last longer than others, we must identify the environments that slow failure itself, not by stopping change, but by stretching it over time. That means turning our attention to the rare conditions that protect continuity. If most attempts at life fail, then survival becomes the real anomaly. Not intelligence, not complexity, but endurance. To persist across billions of years, life requires more than favourable beginnings. It requires environments that change slowly enough for adaptation to keep pace. The first condition is stellar restraint. Stars are the primary sources of energy and instability. Massive stars burn brightly and die violently. Their radiation reshapes entire regions of space. Long-lived stars behave differently. Low-mass stars evolve gradually. Their energy output shifts slowly, often over billions of years. Planets orbiting them are not forced into rapid climate transitions. This gives life time to respond rather than collapse. The second condition is planetary renewal. A planet must remain active long after it forms. Geology matters. Tectonics recycle carbon. Volcanism renews atmospheres. Magnetic fields shield surfaces from stellar radiation. Without these processes, even stable stars cannot save a world. Many planets likely hosted life briefly, only to cool, stagnate, and lose their ability to regulate climate. The third condition is galactic moderation. Life does not exist in isolation from its galaxy. Nearby supernovae, gamma-ray bursts, and galactic interactions impose external limits. Galaxies that evolve gently reduce these risks. They space out explosive events. They avoid frequent mergers. They maintain broad, stable habitable zones. In such galaxies, planetary systems are less likely to be reset by forces beyond their control. The final condition is time itself. Life requires long stretches without interruption. Not millions of years, billions. Any environment that repeatedly crosses biological thresholds, becoming habitable, then hostile, then habitable again, rarely allows complexity to accumulate. The rarest environments are those that remain consistently adequate, not perfect, not static, just stable enough for long enough. When these conditions align, life does not merely survive, it compounds. Each adaptation builds on the last. Complexity accumulates rather than restarting. Biology becomes resilient rather than fragile. These environments are not common. They exist at the intersection of stellar physics, planetary geology, and galactic history, and because they are rare, they define the universe's long-lived biological experiments. Earth may be one of them, not because it is exceptional, but because it has avoided failure long enough to notice itself. This reframes our place in the cosmos. We are not evidence that life is easy. We are evidence that survival is possible but uncommon. To understand how often this alignment occurs, we must widen the scope again. beyond individual planets, beyond galaxies, and examine how often the universe creates environments that can sustain life continuously rather than briefly. When we step back and examine the universe as a whole, a pattern becomes clear. Creation is easy, destruction is easy, survival is not. Stars form naturally wherever gas collapses, planets assemble as a byproduct of stellar birth, organic molecules appear spontaneously under the right conditions. None of this is rare. What is rare is continuity. Most environments capable of producing life are temporary. They flicker into habitability, then fade out again. They cross biological threshold briefly, then retreat beyond them. From this perspective, the universe is generous with beginnings, but stingy with endurance. This changes how we interpret silence. If survival is the rarest outcome, then intelligent life is not limited by the difficulty of emergence, but by the improbability of uninterrupted persistence. A planet may host life for hundreds of millions of years and still fail to cross the threshold into complexity. A biosphere may flourish briefly, then vanish without leaving a trace detectable across space. The universe may be filled with worlds that almost made it, almost stable enough, almost calm enough, almost long-lived enough. Earth crossed that line not because it was designed to, but because it remained within acceptable bounds longer than most. Our star changed slowly. Our planet stayed geologically alive. Our galaxy avoided catastrophic disruption, not perfectly, just long enough. From a statistical standpoint, this places Earth among a minority of outcomes, not miraculous, but improbable. If the universe has tried life many times, then most of those attempts likely ended quietly. No ruins, no signals, no lasting imprint, just chemistry returning to equilibrium. This suggests that the absence of evidence is not evidence of absence. It may be evidence of impermanence. Life may arise often, but fade before it becomes durable enough to be noticed. If so, then the true bottleneck is not intelligence. It is survival across deep time, and that realization reframes the future. If survival is rare, then it is also fragile. Our own experiment is still running. It has not reached a conclusion. The same forces that ended countless attempts elsewhere still apply here, which means the most important question may not be whether life exists elsewhere, but whether any experiment, including our own, can last. Many explanations have been proposed to explain why the universe appears so quiet. Some focus on rarity, others on distance, some on intelligence itself. But when the universe is viewed across its full history, a simpler filter emerges: time. Time is the only factor that applies to every form of life in every environment without exception. No matter how favorable the beginning, no matter how advanced the biology, no matter how sophisticated the technology, time continues to apply pressure. Stars brighten, planets cool, galaxies evolve, energy sources decline. Nothing remains static long enough to guarantee survival indefinitely. This makes time the ultimate test, not whether life can arise, but whether it can endure changing conditions long enough to become noticeable. Many experiments likely passed the first filters. They formed on habitable worlds. They survived early instability. They adapted to local environments. But most may have failed the final one. They ran out of time. A star became too active. A planet lost its atmosphere. A galaxy shifted into a more hostile phase. None of these failures require catastrophe, only gradual drift. From this perspective, intelligence is not the finish line. Longevity is. A civilization that exists for 1,000 years is invisible at cosmic scales. Even one that lasts 1,000,000 years leaves little trace. To be noticed across the galaxy, a civilization must survive not just its own challenges, but the slow, relentless evolution of its environment. This places a severe constraint on detectability. Life may be common, civilizations may arise repeatedly, but overlap in time may be rare. Two experiments can succeed independently and still never encounter each other, simply because they do not exist at the same moment. The universe may not be empty, it may be unsynchronized. This changes how we interpret our own moment. We are not simply asking whether others exist. We are asking whether anyone else is still running the experiment, and that makes the present fragile and significant. Our civilization occupies a narrow slice of time, a brief window between emergence and extinction, between favourable conditions and inevitable change. What matters now is not how many times life has appeared before us. It is whether any experiment anywhere can last long enough to bridge time itself. If the universe has tried life many times, then most of those experiments are already over, not because they failed immediately, but because they could not outlast the forces that shape all cosmic environments. Stars changed, planets aged, galaxies evolved. Time did what it always does. Against that backdrop, one experiment remains in progress. Ours. Earth is not the first place where life could have appeared. It is simply one of the few places where life has lasted long enough to become aware of itself. We did not arrive at the beginning of the story. We arrived somewhere in the middle, after many attempts may have already ended, and before the universe itself grows too old to support complexity easily. This does not make us unique in origin. It makes us rare in continuity. For billions of years, life here survived instability without collapsing completely. It adapted rather than vanished. It persisted long enough to ask questions about its own existence. That persistence is fragile. The same forces that erased countless experiments elsewhere still operate here. Climate change, resource depletion, stellar evolution, galactic timescales beyond human control. Nothing in physics guarantees success. The universe does not preserve life out of sentiment. It allows it conditionally and temporarily, which gives our moment a different meaning. If survival is the rarest outcome, then awareness carries responsibility, not because we are destined to succeed, but because we are among the few experiments still underway. Whether this attempt continues or quietly ends will depend not on cosmic chance alone, but on how well life learns to persist under changing conditions. In that sense, the universe may not be waiting to see if life can appear. It may be waiting to see if life can last. And for now at least, one experiment is still running. When we imagine advanced life in the universe, we imagine intelligence. We picture civilizations that think faster, build higher, and see farther than we do. We imagine knowledge as the final achievement of evolution, but the universe has never rewarded intelligence on its own. For nearly 14 billion years, it has rewarded something else: survival. Long before minds could wonder about their place in the cosmos, life had already learned its most important lesson. Endure, adapt, persist. On Earth, intelligence appeared only after billions of years of trial and error, and even then it arrived late, fragile, dependent on conditions it did not create. Most life that ever existed here never became intelligent, yet it survived far longer than we have. In the universe at large, the pattern may be even clearer. Galaxies change, stars evolve, planets drift in and out of habitability. Civilizations, if they arise at all, must navigate forces far older and more powerful than themselves. Awareness offers no immunity. Technology offers no exemption. The laws of physics do not pause for thought. If the universe has tried life many times, then intelligence may not be the measure of success. Longevity may be. The forms of life that matter most on cosmic timescales may not be the ones that think the deepest, but the ones that last the longest. Tonight we examine a different question, not how smart life can become, but how long it can remain. Because in a universe shaped by time, survival may matter more than intelligence ever could. Across science fiction, philosophy, and even scientific speculation, one assumption appears again and again: that intelligence is the peak of evolution. We measure progress by brain size, by problem-solving ability, by technology, language, and self-awareness. When we search the universe, we search for minds like ours, or more advanced versions of them, but this assumption is rarely examined. On Earth, intelligence is not the dominant outcome of evolution. It is a late development, a narrow branch on a vast biological tree. For more than 3 billion years, life thrived without complex thought. Single-celled organisms reshaped the planet's atmosphere. Simple multicellular life-stabilized ecosystems. Entire biospheres functioned without awareness or intent. Most life that has ever existed on Earth was not intelligent, yet it endured. Intelligence, by contrast, is young. It depends on stable climates, abundant energy, and finely balanced ecosystems. Remove any of these and intelligence collapses quickly. This raises an uncomfortable question. If intelligence were truly the goal of evolution, why does it appear so rarely and so late? Evolution does not plan, it selects. And what it selects for consistently is not insight but persistence. Traits that survive are not those that understand their environment best, but those that remain compatible with it the longest. From this perspective, intelligence may not represent an evolutionary triumph. It may represent a gamble, a strategy that works briefly under specific conditions, but carries risks that simpler forms of life avoid. When we project intelligence onto the universe as the ultimate achievement, we may be projecting our own values rather than nature's priorities. The universe does not ask whether life can think, it tests whether life can continue, and that difference matters. Because if survival, not intelligence, is the primary filter across cosmic time, then our search for advanced civilizations may be fundamentally misdirected. We may be looking for the most conspicuous outcomes, rather than the most successful ones. To understand why intelligence may be common in imagination but rare in reality, we must compare the speed of thinking with the pace of surviving. And that means examining how evolution treats intelligence and endurance very differently. Intelligence evolves quickly, at least by biological standards. On Earth, once the right neurological foundations appeared, cognitive complexity accelerated. Tools emerged, language followed, technology compounded upon itself. In evolutionary terms, this happened almost instantly, but survival operates on a different clock. Life persists not by accelerating, but by stabilizing. The longest-lived organisms on Earth did not evolve rapidly. They refined themselves slowly. They resisted change rather than embracing it. Bacteria, archaea, and simple eukaryotes have endured for billions of years with minimal modification. They survived mass extinctions that erased dominant species. They adapted quietly while entire ecosystems collapsed around them. Intelligence, by contrast, is volatile. It depends on complexity, and complexity multiplies points of failure. A complex nervous system requires steady energy. Advanced cognition depends on stable climates. Technological societies rely on delicate networks that break easily under stress. From an evolutionary perspective, intelligence is not conservative. It pushes boundaries. It increases consumption. It accelerates environmental change. These traits can be advantageous in the short term. They allow rapid problem solving. They enable expansion into new niches, but they also compress timescales. Changes that once unfolded over millions of years are forced into centuries or less. Adaptation struggles to keep up. Feedback loops amplify instability. Survival, in contrast, favors patience. It rewards organisms that minimize disruption to their environment, that recycle resources efficiently, that change slowly enough to remain compatible with long-term conditions. This creates a fundamental tension. Intelligence thrives on speed. Survival thrives on restraint. In a stable environment, the two can coexist briefly. But as conditions shift, restraint often outlasts innovation. From a cosmic perspective, this matters. The universe evolves slowly. Stars change over billions of years. Galaxies shift on timescales that dwarf civilizations. Any form of life that accelerates faster than its environment can tolerate risks shortening its own window of existence. This suggests an unsettling possibility. Intelligence may be common in emergence, but rare in persistence. Many civilizations may rise quickly, only to destabilize the conditions that allow them to exist. If so, intelligence is not filtered out at birth. It is filtered out over time. To understand how this plays out on a cosmic scale, we must examine how the universe treats awareness itself. Because awareness does not grant immunity, and the universe does not slow down for those who notice it. Awareness feels powerful. It allows life to observe its surroundings, to model the future, to imagine outcomes before they occur. From within our own experience, awareness seems like an advantage so great it should guarantee survival. But the universe does not recognize awareness as a special state. Physics does not slow down for understanding. Entropy does not pause for insight. Stars do not burn more gently because they are observed. A planet does not remain habitable because life appreciates it. The forces that shape cosmic environments operate independently of consciousness. A star will brighten whether or not a civilization calculates its trajectory. A galaxy will evolve regardless of how deeply its inhabitants comprehend astrophysics. Climate systems respond to energy flows, not intention. This creates a harsher symmetry. Life can become aware of danger long before it can prevent it. Understanding does not equal control. On Earth, this asymmetry is already visible. We understand climate dynamics in detail. We understand resource limits. We understand ecological feedback loops. And yet understanding alone has not halted destabilization. Awareness reveals risk faster than it enables restraint. From a cosmic perspective, this is not a flaw of intelligence. It is a mismatch of scales. Awareness operates on biological and cultural timescales. The universe operates on physical ones. Even advanced technology cannot fully escape this constraint. Civilizations may delay stellar evolution, buffer against planetary change, or modify local environments, but no technology can stop entropy. No awareness can freeze cosmic time. This means intelligence is always reactive. It responds to changes that have already begun. It adapts to environments it did not design. Survival, by contrast, favors life that never outruns its surroundings. Life that integrates rather than dominates. That stabilizes rather than accelerates. This is why awareness may not be rewarded by the universe. It increases sensitivity without guaranteeing durability. The universe tests life not by asking how well it understands reality, but by how well it remains compatible with reality as it slowly changes. If awareness does not grant protection, then intelligence may carry a hidden risk. It allows life to act faster than the systems that sustain it can absorb. And that may explain why advanced civilizations, even if common, rarely persist long enough to be noticed. To explore that possibility, we must confront an uncomfortable idea. That intelligence may not merely fail to protect life, it may actively shorten the lifespan of the environments that support it. Intelligence does not need hostility to become dangerous. It only needs acceleration. Once a species gains the ability to reshape its environment deliberately, the pace of change shifts dramatically. Processes that once unfolded over geological timescales are compressed into centuries or less. Energy extraction intensifies. Resource flows accelerate. Ecological balances are pushed beyond thresholds they evolved to tolerate. This is not a moral failure. It is a structural one. Intelligent life tends to solve problems locally and immediately. It optimizes for survival in the present moment. It rarely optimizes for compatibility with environments over millions of years. From an evolutionary perspective, this makes sense. Natural selection rewards short-term success. It does not reward foresight beyond immediate reproductive advantage. Technology amplifies this mismatch. Tools allow intelligent species to bypass natural limits temporarily. Fossil energy replaces biological energy. Artificial systems substitute for ecological ones. But bypassing limits is not the same as removing them. The underlying constraints remain. When intelligent life expands faster than its environment can regenerate, it creates instability. When feedback loops are disrupted too quickly, recovery becomes impossible. This leads to self-limitation, not always through dramatic collapse, often through gradual narrowing of options. Habitats degrade, climate systems destabilize, energy becomes harder to extract without further damage. At a certain point, intelligence becomes trapped by the consequences of its own efficiency. This pattern does not require malice war or self-destruction. It emerges naturally from the interaction between cognition technology and finite systems. On cosmic timescales, this matters enormously. A civilization that lasts 10,000 years is impressive by human standards. It is invisible by galactic ones. If intelligent life repeatedly shortens its own window of stability, then advanced civilizations may be common but fleeting. They rise quickly. They transform their environments. They encounter limits they cannot easily reverse. And then they fade, not erased by external catastrophe, but constrained by the momentum of their own success. This reframes the so-called Great Silence. The universe may not be empty of intelligence. It may be full of brief flares, moments when awareness ignites, accelerates, and then subsides. If that is the case, then long-term survival may favor a very different strategy, one that minimizes acceleration, that resists expansion, that integrates intelligence into ecological stability rather than placing it above it, which leads to a radical implication. The longest-lived forms of life in the universe may not be the most intelligent. They may be the most restrained. When we imagine life that lasts, we imagine advancement, bigger brains, greater intelligence, more complex societies. But longevity does not necessarily favor any of these. On Earth, the longest-lived forms of life are not the most complex. They are not the most aware. They are not the most technologically capable. They are the most stable. Bacteria have persisted for billions of years with minimal change. They survive extremes of heat, cold radiation, and chemical hostility. They adapt slowly, but they endure. Complex organisms, by contrast, occupy narrow ecological niches. They require specific conditions. They collapse quickly when those conditions drift. Intelligence amplifies this vulnerability. Advanced cognition requires steady energy input. Complex societies depend on layered systems, agriculture, infrastructure, communication that must all function simultaneously. The more intricate the system, the more fragile it becomes. A small disruption can cascade into failure. From a survival perspective, this is inefficient. Life that lasts may therefore avoid complexity rather than pursue it. It may favor simplicity, redundancy, and restraint. It may spread slowly rather than expand rapidly. It may consume energy conservatively rather than aggressively. Such life would not build cities. It would not transmit signals across space. It would not leave artifacts that survive geological time. It would simply remain. In the universe, this kind of life may be far more common than civilizations. It may inhabit planets quietly for billions of years, never approaching intelligence, never triggering technological acceleration. And if intelligence does arise in such systems, it may be tightly constrained. It may remain local, low energy, integrated into ecological cycles rather than imposed upon them. From our perspective, this life would be almost invisible. We search for technology because it is loud. We search for intelligence because it leaves traces. But the most successful life in the universe may leave none. This forces a reconsideration of what success means. If survival is the measure, then invisibility may be an advantage. If endurance matters most, then restraint may outperform innovation. The universe may not be dominated by civilizations that rise and fall. It may be quietly occupied by forms of life that never felt the need to rise at all, which leads to a startling conclusion. We may be surrounded not by advanced societies, but by survivors. When evolution is measured over deep time, a different pattern emerges. The winners are not the fastest. They are not the smartest. They are not the most transformative. They are the most compatible. Across Earth's history, the organisms that endured longest were those that disturbed their environments the least. They recycled what they consumed. They remained embedded within feedback loops rather than breaking them. They did not dominate. They persisted. On cosmic timescales, this principle likely holds even more strongly. Any form of life that dramatically reshapes its surroundings increases the risk of destabilization. Any system that accelerates change faster than its environment can absorb shortens its own lifespan. The quiet winners of evolution avoid this trap. They exist at low energy levels. They adapt incrementally. They spread slowly, if at all. They leave their host environments largely intact. From a distance, they are indistinguishable from lifeless worlds. Their planets do not glow with artificial light. Their atmospheres do not carry strong technological signatures. Their stars shine as they always have. Nothing calls attention to them, and that may be precisely why they last. If life in the universe often follows this path, then the absence of detectable civilizations is not surprising. The most successful biological strategies do not announce themselves. They do not expand rapidly. They do not seek to be noticed. They simply continue. This suggests a profound shift in perspective. Evolution may not be driving life toward complexity or intelligence. It may be filtering for stability above all else. Civilizations may represent brief deviations from this rule, moments when life experiments with acceleration, abstraction, and control. Most of those experiments may end quickly. leaving behind only quieter forms that persist long after. In this light, the universe's silence becomes easier to understand. It is not empty, it is restrained. Life may be widespread, but successful life may be subtle. Survivors may be common, while civilizations are rare and fleeting. And if that is true, then our search strategy has been inverted. We have been listening for voices, when the universe may be filled with life that never learned to speak loudly. To grasp the full implication of this idea, we must confront what it says about the universe itself, not as a place that selects for intelligence, but as one that selects for endurance. When we listen to the universe, we are listening for noise, radio signals, artificial light, technological footprints that cut sharply against natural backgrounds. But noise is not the same as life. If survival favors restraint, then the universe may be filled with living worlds that never produce signals loud enough to be noticed. Worlds where life remains embedded in local ecosystems, where energy use stays low, where growth never accelerates beyond what the environment can sustain. Such life would not build transmitters. It would not spread rapidly between stars. It would not announce its presence across interstellar space. From our perspective, these worlds appear silent. But silence does not imply absence. It implies compatibility. Civilizations, as we imagine them, represent a particular evolutionary choice. A choice toward abstraction, expansion, and control. One that trades long-term stability for short-term capability. That choice may be viable briefly. It may even arise repeatedly. But it may rarely persist. Survivors, by contrast, make a different choice. Or rather, they never face the choice at all. They remain biological, local, bound to the rhythms of their planet and star. They adapt to change instead of attempting to outpace it. Over billions of years, these forms of life would vastly outnumber civilizations. They would occupy far more habitable worlds. They would persist through stellar and galactic evolution without drawing attention. If this is true, then the universe's apparent emptiness is an illusion created by our expectations. We expect intelligence to look like us. We expect success to announce itself. We expect life to expand outward. But the universe may reward the opposite strategy. Remain small. Remain quiet. Remain compatible. In such a universe, civilizations are not the dominant form of life. They are brief anomalies, experiments that sometimes occur but rarely endure. This reframes the great cosmic question. We are not asking why no one is talking. We are asking why we assumed survival would be loud. And that realization brings the argument back to us. Because if the universe favors survivors over civilizations, then intelligence is not the endpoint of evolution. It is a phase, one that must be navigated carefully or not at all. What matters now is not whether intelligence can arise. It is whether it can learn to behave like a survivor. For humanity, this perspective is uncomfortable. We have come to see intelligence as destiny, as proof of progress, as something the universe was waiting for. But from a cosmic standpoint, intelligence is untested. Our species has existed for only a fraction of a geological moment. Our technological phase spans mere centuries. We have not yet demonstrated endurance. What we have demonstrated is acceleration. We change our environment faster than any life form before us. We extract energy at rates that bypass natural cycles. We alter planetary systems on timescales that ecosystems cannot easily absorb. This does not make us evil, it makes us efficient. But efficiency is not the same as sustainability. On Earth, every long-lived biological system is conservative. It wastes little. It recycles continuously. It remains embedded within feedback loops that limit growth. Human systems tend to do the opposite. We break feedback loops. We externalize costs. We treat stability as an obstacle rather than a requirement. From the universe's point of view, this is not a moral failure. It is a survival risk. If intelligence accelerates change faster than adaptation can keep up, then it shortens its own window of existence. This is the same pattern that may have ended countless experiments elsewhere, not because intelligence is forbidden, but because it is difficult to integrate into long-term equilibrium. If the universe favors survivors, then the question facing humanity is stark. Can intelligence learn to behave like long-lived life? Can a technological species slow itself down without collapsing? Can it limit growth without stagnating? Can it integrate awareness into restraint rather than domination? These are not philosophical questions. They are physical ones. The universe does not care how advanced we become. It only tests whether we remain compatible with the systems that sustain us. If we fail, our disappearance will not be unusual. It will be typical, another brief flare of intelligence, bright, transformative, and short-lived. But if we succeed, the outcome would be rare, not because we were the smartest, but because we learned how to last. Across the universe, life may take many forms. Some may think, some may build, some may never rise beyond chemistry and metabolism. But when measured across cosmic time, these differences blur. What remains is a simpler distinction. Which forms of life endure? The universe does not appear to favour awareness. It does not privilege intelligence. It does not preserve complexity for its own sake. It preserves compatibility. Life that aligns with its environment lasts longer. Life that accelerates beyond it does not. From this perspective, intelligence is neither success nor failure. It is a transition, a moment when life gains the ability to understand the systems that sustain it. Without any guarantee it will respect those systems. Some forms of life may pass through this transition quickly and disappear. Others may never enter at all, remaining stable for billions of years. A rare few may learn to integrate intelligence into long-term survival. Those would be the universe's most successful experiments, not the loudest, not the most expansive, but the most persistent. If such life exists elsewhere, it may not resemble civilizations from our imagination. It may not send signals. It may not build monuments. It may leave no trace detectable across interstellar space. It would simply remain, and if that is true, then the universe is not a graveyard of failed civilizations. It is a landscape shaped by quiet success. Worlds where life learned to last. Galaxies where stability outperformed ambition. Systems where endurance mattered more than awareness. This reframes the question we began with. The question is not whether intelligence is rare. It is whether intelligence can coexist with survival over deep time. For humanity, the answer is not written. Our experiment is still running, and the universe will not judge it by what we know, or how far we reach, or how loudly we speak. It will judge it by how long we remain,